This is Surveyor, my first high power rocket, flying on an H100 White Lightning rocket motor. But for its next flight, it's going to fly on something bigger, like 5 times bigger. It's going to fly higher and faster than anything I've ever built, but that's going to be a problem. See, in the last flight, I barely broke 1,000 feet, but because of the wind, Surveyor landed over half a mile away. If I change nothing, the rocket is going to be blown off the field, break the waiver, and I won't get my next certification. So what do I do? Well, this is where a little thing known as dual deployment comes in handy. My last flight was your standard motor deployment configuration. A delay grain in the motor lights a charge which pops your parachute at apogee. This is dead simple, but also the worst thing you can do on a windy day. When you're doing dual deployment, you use an altimeter which will set off 2 different ejection charges. The first deploys a small drogue parachute at apogee. This just stabilizes the rocket but allows it to fall quickly and get out of the wind. Then at a much lower altitude, the altimeter will set off a second charge to deploy a main parachute. This slows you down for a nice safe landing. Now to make the system work, I need to figure out how to make reliable ejection charges, and that's where this video comes in. I'm going to walk you through all of the testing it took for me to get from this to this. And for those of you who stick around to the end, I'm going to go more in depth on the theory that actually goes into designing these. I'm Hathi, and this is how to over-engineer your ejection charges. So let's start with the propellant. I have just under a pound of Pyrodex P pistol powder. This will work, but it's not the best choice for rocketry. The go-to is 4F black powder, meaning the finest powder available. This Pyrodex is 3F equivalent, meaning it's less fine and will tend to burn slower. There's also some other problems, but we'll get into that later. My first charge was just a latex tube with zip ties to seal the ends. Apparently people have done this with black powder, and I like the idea. In theory, it should inflate like a balloon, allowing the powder to burn, and then it will burst and release a large volume of gas all at once. This is at the very bottom end of the containment spectrum. I want to keep the pressures low because this is just a cardboard rocket, so this seemed like a safe place to start. I set one off and it looked promising. It inflated like a balloon and then it ruptured. I looked at it after the function and it wasn't melted. It actually did rupture, which is a good sign because it should be more consistent. But you can see a problem pretty clearly, which is that a bunch of propellant didn't get lit before it burst. That is a bunch of wasted energy. It kept burning for 700 milliseconds after it burst. For reference, the separation event is tens of milliseconds, so none of that energy is actually going into the separation. When I looked closer at the video, I figured it might be the zip tie making that end too stiff. This would prevent the gas bubble from fully engulfing that propellant and lighting it. To address this, I added extra wadding between the propellant and the zip tie to separate them further and hopefully allow the whole thing to balloon out and all of the propellant to be lit. Somehow, this was even worse. Even less of the propellant got lit. It burned for a full second after it ruptured. This is showing me that it's not the tube being too stiff, it's the tube being too weak. We need to contain it more so that it can build pressure before it ruptures. So I picked up some vinyl tubing which would fit over my latex tubing. This constrains one end of the tube and then the other end is left sticking out. This will cause a bubble of hot gas to move along the vinyl tubing and then finally burst out of the end of the latex tubing. And that worked perfectly. By the time that bubble of hot gas got to the end and ruptured out of the latex tube, all of the propellant was lit, and less than 90 milliseconds later, it was all done burning. Now that's great, but we're not really getting a lot of information here. We're just reading the tea leaves with these open air tests. The whole idea of the ejection charges is to produce a big cloud of gas that pushes the rocket apart. We have no idea how much pressure these are producing. So I moved on to mortar testing. I don't want to put too much wear and tear on my actual rocket. It is, after all, made of cardboard. So instead I got some 4-inch tubing and made a simulated rocket. I wanted this to match my actual separation as closely as possible. So I got a plug, turned it down on the lathe so it would slide freely, and then added a 3D printed extension so that it had the same stroke length as my actual coupler. But this thing is going to take a beating, so I needed to reinforce it. I filled it with a bunch of epoxy and then spun it on the lathe to coat the outside walls and reinforce them. And then I added some ballast in the form of this machined aluminum plug. I did some napkin math and found that the piston needed to be 500 grams. This would mean that when it's being shot out of a static mortar, it is simulating a rocket separating in two different directions in 0G. That's great and all, but this actually didn't work that well. It turns out that this plastic tubing, it's nowhere near perfectly round, meaning there's a big gap around the piston where all of the gas can leak out. What I really should have done is buy an actual body tube for a rocket and an actual coupler and use that as a starting point. But you live and you learn. I added a pressure transducer to the side to measure the pressure inside the mortar. For reference, I'm targeting about 10 psi, so I went with a 30 psi sensor. For the first round of testing, I bought 3 charges. Expecting the propellant to underperform, I started with an aggressive 0.8 grams, but I also brought a 1 gram and a 1.4 gram charge. The idea here is to measure how much changing the propellant loading actually affects performance. Let's start with the smallest charge. Yeah, that was trash. Apparently my aggressive loading wasn't aggressive enough, so I skipped the 1 gram charge and went straight for the 1.4. And that was almost exactly as bad as the first one, so I stood down for the day to reevaluate. Turns out it's a good thing I did, because I recorded no data. I had incorrectly configured my pressure transducer. The only thing I had was the mediocre separation velocity, which was 1.3 and 1.4 meters per second, respectively. Now at this point I could pivot. I could use the larger vinyl tube, fill it with a ton more propellant until I finally hit the performance I want, but I don't want to do that. I should not have to use that much propellant. In theory, I should be using less than half a gram. This is where we start to see the problems with using Pyrodex. With basically all propellants, they burn exponentially faster the more pressure they're under, but these charges are very low pressure. My understanding is that traditional black powder is way less sensitive to the low end of pressure, meaning that these charges would probably work fine if I was using the right propellant. Unfortunately, Pyrodex and other modern smokeless propellants are way more sensitive to the lower end of pressure, meaning they burn extremely slowly if not properly contained. Now, this arguably makes them safer, but it's really working against me here. The real problem I'm running into here is that the latex tubing is bursting way too early, leaving a ton of unburned propellant after each function. If you listen closely, you can even hear it burning several seconds after the mortar has been fired, and a bunch was still left over at the end, which I had to clean out and dispose of. To try to fix this, I took that leftover 1 gram charge and wrapped the end in several layers of electrical tape. This isn't going to be the most consistent method, but what I really needed was a number for how much pressure I can get out of 1 gram of propellant. This is a way to get there. The tape should make the tube stiffer and stronger, both increasing the pressure during the burn and delaying the rupture till later when more of the propellant has been consumed. But being just a couple layers of tape, it shouldn't increase the pressure to a dangerous level. Right? Yikes, that was terrifying. At this point I was pretty glad I was testing in a mortar and not my actual rocket. I should note that I've been very careful when handling these charges. I knew there was theoretically a lot of energy in these things, but it is something else to see one do this. Needless to say, that was way too much energy. The pressure sensor was actually overloaded past 30 psi, which meant I didn't get the one number I wanted out of this test. Thankfully, I did get separation velocity, which across a few frames was an average of 23 meters per second, which allowed me to back calculate the pressure using kinematics and some hacky math, and that got me a reading of 26 psi. That can't be right. Okay, well, like I mentioned, this piston is leaky. There's also some friction I'm not accounting for, so I called it 35 and moved on. Based on that mostly made up pressure, I decided that 0.25 was a good starting point for the next test, and then I also made a 0.2 and a 0.3 so we could interpolate between them and fine-tune our loading. Instead of just wrapping them in tape, I decided to move to a longer piece of vinyl tube. My idea was that this would still constrain the latex, but it would be more consistent than trying to wrap them by hand. I started with the smallest, the 0.2 gram charge, and it really didn't perform. It only produced about 3 psi and the separation velocity was only 3 meters per second. So I moved on to the 0.25 gram charge. This one was perfect. I saw 9 psi and 7.5 meters per second. And finally, I set off the 0.3 gram charge, which did terrible again. Despite having more propellant than the last charge, it produced less pressure, only 3 psi, and the separation velocity was a measly 4.5 meters per second. I chalked this up to sloppy manufacturing. The two underperforming charges seemed to have a bit more latex sticking out of the vinyl tube than the one that actually worked. So for the next set, I was just very deliberate about making sure they were assembled the same. Now, while it's been useful and probably saved me from blowing a hole in the side of Surveyor, the mortar is an imperfect test. It's time to try this in an actual rocket. On the ground, of course. I made a 0.3 gram charge for my drogue parachute and a 0.15 gram charge for my main parachute. The main parachute charge is smaller because the main parachute is bigger, takes up more space, and leaves less room that needs to be pressurized. So I loaded my ejection charges in with my parachutes and propped the rocket up to do some ground testing, starting with my smaller main parachute charge. Wow, that was disappointing. I might have underloaded that one a bit, so let's see if the drogue parachute charge, which is bigger, fares a little better. Okay, so maybe a bit better, but that's not exactly what I'd call a successful separation. And this was the end of the latex tube era. That's right, after 11 tests I decided to scrap the whole thing and start over with a clean sheet design. I need something that bursts reliably at high pressure. Latex is too weak and way too inconsistent. Yes, I could have gone back to wrapping them in tape, but I didn't feel that was a repeatable method, especially because the tape doesn't really like to stick to the latex tubing. Anyway, there's no real need to reinvent the wheel here. Burst discs exist, and they're standard in a ton of different industries, including pyrotechnics. So I made this punch, which allows me to punch a burst disc out of a piece of aluminum tape. Now we just need a body that can hold onto that burst disc and survive the high pressures we're going to. I decided to go with some off-the-shelf flare fittings. The flare is a built-in seal without the need for an O-ring, and the 1/4-inch plug is the perfect size to hold an E-match and about 1/3 of a gram of propellant. I drilled a hole for a nozzle and then added a small spot face where the actual burst disc will sit. Now this is heavier and it also produces a lot more thrust, so I need a way to securely mount it to my avionics bay. Thankfully, JLC 3DP reached out and offered to sponsor one of my projects again. I designed these ultralight custom bulkheads to hold redundant gas generators and this ISOGrid sled to fully replace all of the plywood components in my avionics bay. Despite the extra features, they even came out a little bit lighter than the original hardware. Once again, JLC 3DP has knocked it out of the park. The quality of these parts is perfect. The detail on my logo is flawless down to less than a millimeter. I made these from one of their newer materials, PA11 HP nylon, which is stronger and tougher than the PA12 nylon that I used for my bend test fixture. Just look at the elongation difference. The PA12 fractures at 20% elongation, but PA11 will hold on up to 50% elongation. So, while I wouldn't say these are stronger than steel, the material properties are excellent, and these are definitely flight ready for my L2 certification. But don't get me wrong, I did take a long hard look at that titanium 3D print option. One day. I also want to take a moment to talk about JLC 3DP's service. When I sent them these parts, an actual person responded to me and said, hey, you might have a problem with surface finish in these areas. That's right, every part you send them is reviewed by an actual engineer. But of course, these parts are just going to get blasted by ejection charges, so I gave them a thumbs up. You know, the barely noticeable layer lines on the back of the bulkheads are not going to cause an issue. So once again, thank you to JLC 3DP for taking my rocket to the next level, and if you want to take your project up a notch, check out the link in the description to save $70 as a new user. Alright, now back to testing. This was my first test of this extremely over-engineered charge cannon. And it looked pretty promising. The burst disc burst and shot out a big cloud of gas all at once. Now you can see that there was some powder left over, still burning, but that's to be expected. If all of the powder burned before it burst, obviously it wouldn't burst. But again, there's only so much we can learn from an open air test, so I pulled the mortar back out of storage and gave it another try. Well, that was disappointing. But wait, this is one of the benefits of a burst disc. By using a thicker disc, we increase the pressure and increase my efficiency. I moved from 1 to 3 tape seals, based purely on vibes, and it worked beautifully. Finally. Unfortunately, I didn't get pressure again. It seems that this cheap pressure sensor didn't like the hot corrosive gases that it was being exposed to, and something inside it is toast. I tried to protect it with grease, but apparently that wasn't enough. Thankfully, at this point, I did have a few good reference points where I had pressure and velocity, so I was able to refine my simulation and back calculate pressure again. Based on that, we're around 11.5 psi, which is perfect. And finally, it was time to give this another shot in Surveyor. I used an early FDM prototype of the mount that I sent to JLC 3DP to hold both charges at once. This is the first time that my redundant charge is going to be exposed to the firing of my primary charge. I didn't expect it to be a problem, but just to be safe, I did try it out in the larger of the two volumes, the drogue separation. Ah, a thing of beauty. For once, I was not foreshadowing a problem with the test. That second charge held up fine. The burst disc was completely untouched by the blast. Also, in the video, you can see that that charge is still firing as it separates. This means that if we really wanted to, we could get more juice out of this thing by putting in a stronger burst disc. Now to flip it around and try my main deployment. Now that was powerful. It even started to release the parachute, which, hang on.
Oh my god.
Yeah, so when I said there was less empty space in the main parachute compartment, I should have been more specific. There's literally zero empty space. I actually had to cut into my nose cone and add a new bulkhead just to fit the parachute in here. And that parachute was pushed right up against the nozzle of the gas generator, which just blew a hole straight through the flame protector, charring my leader lines, which, if you don't know, are pretty important. Now this would have worked, it would have separated, the parachute would have deployed, but another shot or two and that parachute's going to start to look like Swiss cheese, so I need to fix this. I need some kind of piston between the gas generator and the parachute. I actually haven't done it yet at time of recording, so I'm going to hand it over to future me to see how that went. Hello again, it's me from the future. I decided to just buy a 3-inch PVC pipe cap. It's a little undersized for the inside of a 4-inch rocket, but it is just large enough to fit over the gas generators and strong enough to absorb the blast. All I had to do was drill a hole that could fit my shot cord, and we were ready to test. By this point, I had the fully 3D printed avionics bay from JLC 3DP, so I went ahead and tested that as well. I tried hot gluing the gas generator to the mount, but the hot glue really didn't like to stick to the nylon, so I resorted to blue painter's tape. Obviously, this isn't ideal for flight, but it's gonna have to work for now. But there's nothing left to do but give this another shot and hopefully not punch a hole in my parachute. That worked beautifully. Honestly, it looked way more energetic. The shock cord got snapped tight, the breakaway tape seams ripped and absorbed the shock. This is exactly what a deployment test is supposed to look like. But at this point, I did notice something interesting. I was going back and calculating separation velocity for the first two tests. The first test with the drogue deployment was much slower, not really surprising because it's much heavier, but the interesting thing was when I converted that to kinetic energy, they were almost identical, within 1.2% of each other. This is great because it means my gas generators are introducing a fairly consistent amount of energy. Right? Well, when I went back and compared this to my mortar testing, that last mortar test had significantly more energy than the deployment test. And more telling, when I looked at the third deployment test using the piston, it also had a much higher energy, much closer to the mortar test than the first two deployment tests. Now, some of that efficiency increase is almost certainly thanks to the piston increasing the effective stiffness of the parachute pack, but there's something else going on here, and to understand it, we're gonna have to go a little deeper into the theory of ejection charges. I've obviously touched on this, but let's start at the very beginning. The idea of an ejection charge is to introduce a bunch of pressure to push your rocket apart and deploy your parachutes. Now, to address a possible comment people have, you don't necessarily have to achieve this through combustion. A lot of people use high-pressure cold gas, like CO2 cartridges, to deploy their parachutes. I think there's an impression that pyrotechnics are low-tech, but really they're state-of-the-art. I'm pretty confident that every crew-rated spacecraft flying today is using hot gas generators to deploy their parachutes, which probably don't look that different from what I've designed here. Obviously different propellant and much larger. When you take a closer look, the advantages are obvious. A cold gas system requires a large reservoir, a high-speed, high-flow rate valve, which can be remotely triggered. They're complex, they're bulky, and worst of all, they're heavy. Let me remind you that this was 1 gram of propellant, a couple inches of tubing, and tape. Imagine the size of the CO2 system you would need to match that. These charges work with 2 wires and no moving parts. They're shelf-stable, they're shock and vibe resistant, and they pack a huge punch into a tiny package. Now yes, that can make them dangerous, but if you're old enough to buy these materials, you're an adult. Read up on what you're doing, read the warning labels on the packages, and at the very least, don't point them at yourself. These are explosives. I don't want to hear, oh, it's just a deflagration. A deflagration is an explosion. The only difference between a deflagration and a detonation is that a detonation occurs faster than the speed of sound in your propellant. But of course, both of those can be faster than your brain can process information, and your fingers and eyeballs don't really care about the technicalities. Okay, with that out of the way, let's talk about the math that actually goes into designing your ejection charges. Don't worry, it's fairly simple once you've walked through it, and there's plenty of online calculators to help you out. You just need to plug in the size of your rocket, the pressure you want to hit, and it will spit out a massive black powder. Now, as I've demonstrated about a dozen times, this doesn't always work, so it's best to test it on the ground instead of 1,000 feet over everybody's heads. Now, this is the equation that these calculators are using. It looks kind of fancy, kind of cursed, but really it's not that complicated. That first bit is just converting between pounds and grams because we used mixed units in rocketry. Sorry, not sorry, the same thing happens in industry too. What if we drop that term and rearrange it? It turns out this is just your ideal gas law, the same thing you learned in high school or maybe earlier. This is PV equals MRT. Your pressure times your volume equals your mass times your gas constant times your temperature. Now this does mean that that R is going to be specific to the type of propellant you're using, but it's probably fairly similar between Pyrodex and black powder, and the temperature of the gas is also probably about the same. The big thing this equation is missing is efficiency. My early charges left a ton of unburned propellant, meaning that the mass of gas was significantly lower than the mass of propellant that I put in the charge. Now you can fix this by just adding more propellant, but I chose to go the other route, which is increased efficiency, by burning more of the propellant before I release all the gas. But now that you've produced your hot gas, you can look at the other side of the equation. You're getting a certain amount of PV out. For a specific charge, PV should be roughly constant, meaning that in a small volume, you'll get a high pressure, and in a large volume, you'll get a low pressure. And that's the number I was chasing in those first mortar tests. I wanted to figure out how much PV I could get out of 1 gram of Pyrodex. And by taking those measurements from a mortar, which closely matches my actual rocket, I was able to account for any of the inefficiencies that come from a slow burn rate or expansion or heat loss, things which are basically impossible to measure directly. Once I got that number for my best performing latex tube test, I knew I had the right amount of propellant. I just needed to work on reliability. For my first flight, all I had to do was use the provided black powder. It's super fine, super fast burning. I just put a rubber cap over it and it worked perfectly. Pyrodex is less fine and also more sensitive to the low end of pressure, so it needs to be contained, pre-burned, and then released all at once. Obviously, I chose to use a burst disc in my gas generator, but you can get a similar effect using shear pins, little plastic screws which hold your stages together and then shear off under pressure. The reason I'm not using those is because this is cardboard and I'm a little worried they would rip through it, but if it was fiberglass, that would be the obvious way to go. When we're using these kinds of systems, we really need to change the way we're thinking about sizing our ejection charges. In the calculator, it's treated like M is the mass of your propellant, but really it's the mass of propellant that manages to burn before your burst disc or your shear pins fail. And to control that, we don't necessarily need to change the mass of the propellant. We just need to change the strength of the frangible component. Now remember that constant PV assumption? That isn't just for different sized chambers in my rocket. I can actually use that to back calculate the pressure in my ejection charge using the mortar test. My last mortar test was probably about 11.5 psi and a roughly 70 cubic inch volume. So if we back calculate the pressure in my gas generator, it's 17,000 psi. Now, I don't necessarily think that's a real number. We're definitely overestimating our pressure because the nozzle of the gas generator is concentrating all the flow on the back of the piston. But it is a pretty good indication that we're overloading these fittings and that I should continue to be careful when handling them. And it also tells me that I shouldn't be making that burst disc any stronger. If I need more impetus in the future, I'm just going to move to a larger volume, which increases my PV, without increasing my pressure. And that is finally what allows us to explain the issue that started this whole discussion. I didn't mention it at the time, but between that last mortar test and that first deployment test, I changed the way I was sealing my initiator into my gas generator. For the mortar test, I was hot gluing the leads on the outside of the gas generator. This didn't seal super well, and it also left a glob, which would make it harder to mount. So for the deployment test, I pivoted to putting a glob of hot glue on the initiator before I put it into the gas generator. This little ball of hot glue, I hoped, would plug up the bottom and prevent it from leaking. It didn't work super well, so I also added a bit of super glue to the outside. That was a mistake. It was such a pain to remove. Now, the unintended consequence was that that glob of hot glue took up some of the ullage volume in my gas generator, meaning that once I added my 0.3 grams of propellant, it was basically filled right up to the brim. Now that you've seen the equation, you can see the problem. My volume went down, but my pressure stayed the same because my burst disk is the same. That means that the burst disk fails a little bit earlier and a little bit less propellant is burned. The result was that less gas was released, and there was a 60% reduction in energy for those 2 deployment tests. Now, like I mentioned, that glob of hot glue didn't even help it seal, so I left it off for that final piston test. Yes, I knew this would increase performance, but I hadn't run the numbers yet, so I wasn't necessarily expecting a 300% increase. It turns out that the combination of that piston and the unintentional improvement to my gas generator resulted in quite the separation velocity. Not that I'm complaining. Now, this is enough to understand the basics of designing ejection charges, but it really is just scratching the surface. First, the heat loss. If your gas has to flow around complex paths or over cold metal, it's going to suck heat out of it, and that's going to take energy out of your deployment. Also, there's the whole phenomenon of secondary combustion. Black powder contains its own oxidizer. It's going to react even without air, but that reaction releases a bunch of hot gas, which can react with oxygen in the air and break down further. This does manifest in rocketry, specifically ultra-high altitude rocketry. When there's little to no air in your parachute compartments, you're going to lose that boost from secondary combustion, and people have found that you have to add significantly more propellant to make up for it. That's just another reason that it's probably a good idea to intentionally oversize your ejection charges a little bit. My Apogee deployment test, that first one, was actually a little bit weaker than I wanted, but I think with this improvement to the gas generator and the fact that I'm not going to super high altitudes, I think I'm going to be just fine. If you want to find out, subscribe. The flight should be happening in about a month or 2. And for now, I'm Khan Hathi, and I'll see you in the next video.